All right. We should be moving on to question 5, but I have to admit that I failed to actually understand question 5, the solution of which is in the website. If you go to the website, I couldn't understand the solution, and I suppose some of you would be able to understand it. The website is, in fact, all these problems, the solutions are there in the website, except that they are just given as text solutions without any verbal uh, input. And that is one of the reasons why I am doing this exercise, so that you can see the solutions as we go along. Um, so if you look at these the SAMO solutions, you have to register SAMO and go into 2023 senior round 3. Number 5, you'll be able to see the solution. And I couldn't understand the solution, so I'm not able to speak about it. Okay, so we go on to question 6. And even this too, it took me a very long time to understand the solution, and I will try my best to unpack it so that it becomes somewhat clear. Okay, so we go into question 6, which you see on the screen. This question, it says, let me just speak about this question before we get on to it. One of the early tricks in solving a right angle triangle, the theorem of Pythagoras in particular, is when you got a right angle triangle, we know that the square on the hypotenuse is equal to the sum of the squares on the other two sides. But actually, the way to prove that, one of the ways to prove that geometrically, is to show that the area of this square is equal to the sum of the areas of the squares which are drawn on the other two sides. So if you show this, the area is equal to this plus this area, it's the same as showing that the square on the hypotenuse is equal to the sum of the squares on the other two sides. So this is in the case of a right angle triangle, and this trick was used. I don't know if the ancient Greeks used that method, but whatever it is, this is one of the many, many ways of proving the theorem of Pythagoras. Subsequently, there were many other proofs. Okay, so that's one. And then people try to extend this and say, well, let's draw things on a triangle. It need not be a right angle triangle. And they took, for instance, they took a random triangle. Oh, sorry. Took a random triangle, and instead of constructing regular quadrilaterals, a square is a regular quadrilateral. They said, why don't you try putting a regular triangle? A regular triangle, all the sides are equal, is an equilateral triangle. So this became another interesting thing to investigate. And a mathematician called Fermat, I think you may have heard of him because his theorem Fermat's last theorem is very famous. But he also did some work in geometry. And one of the things Fermat investigated was where you draw equilateral triangles on the three sides. Then he noticed something quite interesting, that when you join each vertex of your original triangle to the opposing vertex of the equilateral triangle, he found that these three lines, they all are concurrent. They went through the same point. See? And this point, in his honor, this point is named where these three lines meet. This point is named as the Fermat point, where these three equilateral triangles and these like diagonals intersect at one point. Okay, so this is another interesting point. Actually, it turns out that all these three angles from here, if you those three angles that you get all turn out to be 120 degrees. They're all equal. Yeah, see? From the Fermat point, all 120 degrees. And also, this is an interesting point in that if you take any other point and if you join it to the three vertices, like this one, and if you add those three distances, that distance is always greater than this one here. This particular distance, this plus this plus this, is smaller than any other distances taken from any other point. So if you take another point like this, and if you draw the three distances from here to the vertices of your triangle, and if you add these three numbers, that number is greater than the sum of the three red ones. So Fermat point is good. So it's very interesting, and some of you should go and read about that and try to understand more about this very interesting point. Okay. So then somebody said, okay, why don't we draw rectangles? But now the rectangle they drew is not any special rectangle, they're random rectangles. So that made these things even more complicated. What can we say? All right, so this particular problem here deals with that issue where you're drawing, you've got a triangle ABC, as you can see, the original triangle, and you've got three rectangles drawn on the three sides. And some researchers were investigating this to see whether you still have concurrency. And they found, yes, you do have a concurrency theorem where you have to repeat some angles. If you take this angle here, which is formed between the diagonal and the side of this rectangle, and if you copy it on that rectangle there, and you do the same thing, you take this angle here, which is formed between the diagonal and the side of this rectangle, and you copy it on the other side of that, and you join them. This point here, this new point, then becomes an interesting point, because if you take these two opposite vertices of these two rectangles, F and I, and you join them, and here too, you take the two opposite vertices of these two rectangles here, and you join them, they meet at this place. It turns out that this point here, which we just constructed, when you join the third point to S, it goes through the point of intersection. So these three lines are concurrent. So that is what we are asked to prove. Prove that these three lines are actually concurrent. I have to tell you, it's a very difficult problem. I took many hours to even understand it. And the reason for that was that the proof of this is not in Euclidean geometry. Euclidean geometry is the geometry that you deal with in school. But there are other geometries apart from Euclidean geometry, and one of them is called projective geometry. And to prove this, you require a theorem from projective geometry. So in a way, this problem occurring in round 3 of SAMO will be quite out of the reach of most South African learners. It's a kind of a problem that can occur in the International Mathematics Olympiad, where you have to know far more than what you do at school. But I guess the people who set this problem expected those who are going into round 3 to also learn something about projective geometry. Okay, so there's a particular theorem in projective geometry that is invoked to solve this problem. So in projective geometry, this business of concurrency of lines and also collinearity of points. In other words, 3 points lying on the same line, those points are called collinear. And if 3 lines intersect at the same point, then they are called concurrent. So these kind of concepts are very important in projective geometry. And one major theorem in projective geometry speaks about this. It speaks about the concurrency like this now, concurrency of lines. Okay, and the actual theorem is if you've got a circle, and if you take 6 points on the circle, six random points, right? Then it turns out that if you name these points in order, let's name them A, B, C, D, E, F. Now, this is you get a hexagon because there are 6 points, gives you a hexagon, right? In an hexagon, you've got opposite sides. So you got this pair of opposite sides. So you got a side, miss a point, side, miss a point, and you come back to that. Okay, so that's a pair of opposite sides. And you also have 3 pairs of such opposite sides. Take BC. And the side opposite it, you miss a point at EF. There's another pair of opposite sides. And then there is one final pair, which is left. And that is CD and AF. Okay, so if you take these pairs of opposite sides and extend them or produce them, as I said earlier on, right, then they should meet three intersection points. Right? Now, this theorem in projective geometry says that if you take the opposite sides and you extend them and then meet the red lines, you meet at some point, the blue lines meet at some point, the black lines meet at some point. Those 3 points, those 3 intersection points are collinear. They lie on the same line. Right? Now, you may say, but wait a minute, the way these lines look, they are parallel, some of them, and they don't meet. But in projective geometry, interestingly enough, all lines meet. They dropped the parallel axiom and they said that any 2 lines meet, right? But they meet at some point which we call infinity. Right? You may question that, but they justify it in some way. And these points meeting, wherever they meet, so that becomes a point of intersection. So the infinity becomes a point, in ordinary language. Because parallel lines, they so-called meet at infinity. And in projective geometry, infinity becomes a single point. And that single point, every line extended meets at that point. Any 2 lines meet at infinity. All right. So, well, I mean, some of them do not meet at infinity, but those parallel lines will meet there. Okay, so infinity also becomes a point. So in that respect, now you got that point and the other ones which do meet, those 2 points, and of course, they will always be collinear with infinity because infinity contains every other point. But the problem becomes interesting when you have these lines are not parallel and they will meet. Like, for instance, um, so here is what I was saying. So here you have the 6 points. I've got a small circle here because sometimes it's quite difficult to make these lines meet. So I've got a small circle. And when you draw the opposite sides, as I have indicated, you'll notice that the 3 intersection points lie on the same straight line. They are collinear. Okay. Now, the fascinating thing about this is that you don't have to take these points in this order. You can take these points anyhow you want, right? But what is important is that if I read these points in order, A, B, C, D, E, F, A, B, C, D, E, F, right? Then, as I said, the opposite sides become A, B, miss a point, D, E. So you got A, B, D, E, and they will meet at some point. So we can say, we use a symbol here, intersection. This is a symbol for intersection in sets. And where these 2 lines meet, this is a single point. And then you take the next pair of opposite signs, it'll be BC, this is a point EF, intersection EF. That's another point. And then AB, BC, and then you have CD. CD, miss a point. We normally bring back the A in the front. So you have, what do we say? CD, miss a point, FA. So this is the third point. And there it is, you have your A, B, D, E, B, C, E, F, C, D, F, A. Those 3 points, they are collinear. But when you write it down like this, then you can write it down quite nicely. But make sure you bring the A at the end so that you have your CD blank FA. Okay, now as I said, it doesn't really matter how you choose these points. You can choose these points in some other way. Like I could have chosen BDAECF. See, could have chosen it like that. BDAECF, and then you come back to B. Now these are just 6 points. This is what you call a crossed hexagon. But it's a cyclic hexagon because all the points must lie on a circle for this theorem to hold. So now see, now this hexagon is B D C E. I'm sorry, B D A E C F. So yeah, B D A E C F, and that's very, what do you call a cross hexagon. You can hardly see the hexagon, and more than that, it's very difficult to see the opposite sides. But if you use that method which I did now, the opposite sides in Swanya will become BD intersect EC, there it is, DA intersect CF, there it is, and the next one will be AE, BDA, AE, this is a point, FB. So those 3 points, when you take their intersections, they will lie on the same straight line. And there, I've actually drawn those intersections in these 3 red dots, and you will see that those 3 points are collinear. Quite a beautiful result that is coming from projective geometry. You can't use ordinary geometry, I think, to prove such a beautiful result. Anyway, so I had to go and study projective geometry to understand the solution to this problem. That's why it took me a long time, and I can explain it to you as I have done now. Okay, so that's a theorem that we will use somewhere along the line. Okay, now comes this very complicated diagram. Bingo. All right. So let's just keep track of what we are doing here. The original triangle ABC, I've shaded it in gray, right? And then we draw the 3 rectangles. You can see on this side, the rectangle is quite clear. This rectangle is quite clear. And this rectangle here is quite clear also, right? And then we said we join this one point here, one corner of the rectangle, to that one there. So HE is what we have drawn. That's one of the lines. Then we said you take from here, you take from this rectangle, you join it, the vertex of the other one. So that's FI. So H goes to E, I goes to F. And then we said, then this new point, C, we created this point here, S, using these angles. Then we said that CS, right, that these 3 lines, they are concurrent. Now, at least, yeah, okay. So essentially, Yeah, I had to prove that these three, the intersection points are all lie on the same straight line. The intersection points are that one, right? CS, and then HE and FI, HE and FI, FI, and it's a little point here. I'm just putting that, I hope you can see that, right? It's where the blue and the yellow small triangles meet. So that's another intersection point. And C, CS. And to show that these 3 points are concurrent. Now, they all lie on the same straight line. And I just described a theorem where 3 lines are concurrent, but they have to be points which are intersection points of sides of a cyclic hexagon. Now, this red circle here was not there. I've just drawn it in. So let's ignore that circle for the moment. And then you say, well, if I'm going to use the theorem, I need to have a cyclic hexagon. I don't even have a circle to start off with. That's why this problem is quite difficult. And then by examining this, you'll see that HE and FI, you see, those 2 points, H and I, they are both on the same rectangle. So it suggests that this circle that we have contains H and I. See? The other points, E is just a single point in this rectangle, HE, and F is just 1 point. And as far as C and S are concerned, C is 1 point on 2 rectangles, and S is not even on any rectangle. So H and I seem to be, this H and I seem to feature as points on the circle. Now, is it a circle which contains H and I? Well, HI is a side of a rectangle, and any rectangle is cyclic. Any rectangle. Because the opposite angles are supplementary. So every rectangle is cyclic. If you want to know where the center is, well, it's very simple. The center is, for a rectangle, you can write down the center straight away. It's where the 2 diagonals meet, because a rectangle is a parallelogram, and the diagonals are equal, and they intersect, they bisect each other, because it's a parallelogram. So all these are equal. Diagonals bisect each other, but they're all equal because the diagonals themselves are equal. So it means if I choose this as a center, that circle will go through those 4 points. So the center of the circle, the circumscribed circle of a rectangle, is where the 2 diagonals meet. So I've drawn these 2 diagonals here, and this is going to be the center. See? And when you draw the center, as you can see, that center contains I, H, A, and B. I mean the circle. Right. So I've drawn the full circle. Unfortunately, only 2 of these 6 points are on the circle. Right? You need to get 4 other points. Okay. And the way to get those 4 points is, now you look at CS. Okay, let's not look at CS. We look at HE. HE. HE, let it cut the circle at the point L. So you got HLE is a straight line, and L is on the circle. So I got H, I got E, and I got L. Likewise, the other one is Fi. Where is F? Fi. Where does it cut the circle? It cuts the circle at this point here. We call that K. So now I've got 4 points. I need to have 2 more points. And then these points actually must have the S in it. So what we do is we extend. It turns out that this point here is not on that circle. But if you extend it and extend this, then you get 2 points, 2 new points on the circle. So M and N. So you have these 6 points which lie on the circle. All right. So now we've got our cyclic hexagon, and we can use our theorem to try to prove that these are that the 3 points in question are concurrent. So what we actually do is we know that I is on the circle because, why do I say E? It's HI. Okay, H and I on the circle, A and M on the circle. Right, now, let me just get myself sorted out here. So the points that we want to look at are the red points here. N, M, I, right? The N and M are the new points. H and I were the original points, and K and L. So K and L, M and N, and H and I. So those are the 6 points that I want to look at. And I can see that some of these points are intersection points. Like for instance, HI intersect HM, these red lines, is S. And that's one of the points which is a point of collinearity. Another point of collinearity is this one here. And this is, if you look at this, you'll see it's IK, look at the red lines, IK and HL, they intersect at this point. So those will be 2 points on the cyclic hexagon, right? And you know that IK, all these are straight lines. Now you've got a third one, which is C, but C is the only problem here is that C, S, we don't know whether this is a straight line. See, so what we have to do is we look at CKM. C is the intersect of KM and HL, but we don't know that. We don't know that C is the intersection point of HMK and HL. So I need to show that CKM is a straight line. CKM, and the other one is CLN. Are these straight lines? So we don't know that. It's like asking whether K belongs to the line CM. All right, so this is what I'm going to show now. Okay. We'll just ignore all the other things that we have said. Let me So what I want to show is the following. Let's just try to show this one here. C required to prove that CKM is a straight line. Right, because I want this point here, C, to be one of the 3 points which are collinear, right? It'll become clear a little bit later on, in case you got lost. Now, how do I show the CKM is a straight line? We already know that FKI is a straight line. That's given because the reason for that is we said that K is the point where Fi intersects the circle. So obviously K is on Fi. It's a point of intersection. Right. So we know that FKI is a straight line. And we want to show that CKM, and there's your K here. I want to show CKM is a straight line. Now, if you look at FKI, I got this angle here in between here. We know that one line is straight, but we don't know that the other line is straight. But I know that these two lines here, they intersect at this angle. I put alpha here. Have I got any reason to put alpha? Because alpha is a known angle here. All right, let's say why I put alpha. Okay, if I look at these two lines here, they intersect at K on the circumference. Now, which chord of the circle subtends this angle alpha? If you go up to Ki, you go to Km, and you will see it's this chord here. Mi subtends alpha at K on the circle. Now, you know that angles in the same segment are equal. I shouldn't have called this alpha. We don't know that this is alpha. Right? So it's for the moment, let's just take this thing off. This angle is subtended by Mi. Is there any other angle subtended by Mi on the circumference? So you go up here and you go right up to the circumference, H, and you come back to I, and lo and behold, it's this angle here which we already know to be alpha. So Mi subtends alpha at this point, and since these 4 points lie on the circle, this angle is alpha. So I can say that this angle here is alpha. Right. Okay, now I've got one angle on this. If I want to show, I already got one straight line. If I want to show that the other one is a straight line, then I have to show that vertically opposite angles are equal. If I can show that these two angles are equal, X and Y, if I can show that they are equal, I already know that this is a straight line. So these two add up to 180. So therefore, I know these two are equal, then those two add up to 180, which makes this into a straight line. So all you need to do show is the vertically opposite angles are equal. So the vertically angle which is vertically opposite to alpha is FKC. FKC. And now the question is, if FKC also equal to alpha? So that is the challenge now. All right, so how do you do that now? You see, FKC, right? Now these points are not on a circle anymore. C and F, they are not on my red circle. But I need to find out whether FKC is equal to alpha. But I know that this angle here is alpha. It's given. This is how these things are constructed. And I'm asking whether FKC is alpha. But if you look at this, you'll see FC subtends alpha here, and the same line subtends the angle we are investigating, FKC. So for this to be alpha, we are asking the question, are these points on a circle? Are these points concyclic? So in other words, we're talking about AK, CF. The concyclic means they lie on the same circle. Or otherwise, AKCF is that a cyclic quadrilateral? Now we don't know that. So let's examine those 4 points. That one, that one, that one, and that one. And you'll see that AF subtends 90 degrees here at C. All right, so we will know that they are concyclic if we know that AF subtends 90 degrees also at K. So I didn't draw that because it's so complicated. I'm going to draw it now. What I'm going to draw is I'm going to draw AK. And I'm asking whether AKF is 90 degrees. Is AKF. If I know that AKF is 90 degrees, then I can conclude that these are concyclic. All right. Now we know that this is a straight line, right? We said that Fi is a straight line, so FKI. So it's the same as asking whether AKI is AKI equal to 90 degrees. But wait a minute. K, I, and A are now on the circle. When we're asking whether it's 90 degrees, so we're asking whether AI is a diameter of the circle. And yes, AI is a diameter of the circle, because when he drew the circle, we said that the center is where these two diagonals intersect. So this must be the diameter. So AI is a diameter. Okay? So we worked backwards now. So if you want to prove it in a proper way, you'll start like this. I'm not writing it down, so listen carefully. You'll say AI is the diameter of the circle which we have drawn. Reason is it subtends 90 degrees at the circumference. It subtends this right angle. AI is the diameter. And therefore, AKI is 90 degrees because K is also in the circumference. Then you will say, we're working backwards now, you see. You say, therefore, AKF is 90 degrees because this is a straight line. We know this is a straight line. So AKF is 90 degrees, but AKF is equal to A, therefore AKF equals ACF. Because we know that this is 90 degrees. This is the angle in a rectangle. But the moment you have that, that means these two angles are subtended by AF are equal, and therefore you can conclude that AKCF is concyclic. But the moment you can conclude that it's concyclic, then you can say that CF subtends equal angles at A and K. So, but CF subtends alpha at A, therefore CF subtends alpha at K. So in short, this angle here is alpha. But now these are vertically opposite angles, you see. That's what we needed to show. If FKC is equal to alpha, right? We have just shown it. So all this actually proves that CKM is a straight line. So we proved it, right? Now, that is just one part. We can, in a similar way, but I'm going to do it. Now we need to show CKM is a straight line. We also need to show that CLN is a straight line. So now we're going to show that CLN is a straight line. CLN. Let me just wipe out all these other things that I have done here. Right. Now I'm ready to show that CLN is a straight line. So let's look at CLN. Okay, I don't know that's a straight line, but I do know that HLE is a straight line. Because by construction, we said that HE cuts the circle at L. That we know is a straight line. So now we got HL. Now we are focusing on L here, right? And we want to show that we know that HLE is a straight line. We want to show that CLN is a straight line. So again, we try to show that vertically opposite angles are equal. And we start with this angle here. And you notice that I put a beta here. Am I allowed to do that? So let's take this thing off. And we say, let's look at this angle here. Is it equal to beta? Because beta is a given angle. We said this angle here is beta. See? So, and we said this angle here is beta. So let's have a look at this point here. No, I'm sorry. Yeah, this point. Now, we need to know which chord of the circle, this is a point on the circumference, which chord of the circle subtends this angle that we are investigating. So you go up there, and there's one end, and then you go up on the other line, and you go to the other end. So the chord that you're looking at is HN. HN subtends this unknown angle at L. L is in the circumference. Now, does HN subtend any known angle in the circumference? And yes, it's this angle here, because I is on the circumference. So NIH is subtended by HN, but this angle is beta. Therefore, this angle has to be beta. All right, so we got one angle is beta. Now we have to try to show that this other vertically opposite angle is also beta. So the question is now, is CLE equal to beta? CLE, is it equal to beta? Now, we have beta is also this angle here. All right, we know that CE subtends angle beta at B, and we want to find out whether the same thing subtends angle beta at L. So the question now is CLBE, are they concyclic? If we know if they are concyclic, it's the same kind of argument as before, but we are now following the beta route. So CLB and E, are they concyclic? Okay. Do they all lie on a circle? If they do, then I can say that this angle is beta, and that's exactly what I want to prove. And again, now you'll see that BE, if you take CLB, these are the four, C, E, L. Those are the 4 points that we're investigating. If you look at BE, it subtends 90 degrees at C. So the question is, does it subtend 90 degrees at L also? If we can do that, then we can say, yes, is a concyclic. So we have to look at BLE, and we are asking the question. Let me just remove this other line that I've drawn. Right. So I'm asking the question, is BL, we know that BLE, we're asking whether BLE is a right angle. Now we already know that this is a straight line. So it's like asking whether this other angle is a right angle. Now this point here is on the circumference and you've got a right angle at the circumference. So you have to see whether it is subtended by a diameter. If you go up to that and you go up to that point on the circumference and join them, lo and behold, you've got the diameter. Right? Because now we're looking at the other diameter of the rectangle, and this diameter will subtend 90 degrees. So if we want to prove that this angle is beta, again, we work backwards. We'll say HB is the diameter of the circle, right? Because by construction, this center of the circle is on HB. So HB is the diameter. Therefore, it subtends 90 degrees at L. So this angle is 90 degrees. And therefore, these two angles are supplementary because this is a straight line. So this angle is 90 degrees. But BLE is now a right angle. It's now equal to BCE, which we know to be a right angle because this is an angle in a rectangle. So BE subtends equal angles at L and C. So therefore, these are concyclic. Now, the moment you know they are concyclic, then every side, CE, subtends equal angles at the other points. So CE subtends beta at B, therefore it must subtend beta at L. So that means CLE is beta. Yes. And now we have that the vertically opposite angles are equal. So this is a straight line. So we have now proved that CLN is also a straight line. Okay, that took a lot of beating because what was given, that alpha and beta, it didn't look as if they were related. But in the end, it's quite beautiful. All right, so now what do we have? We have all these lines are straight now, right? So I'm now going to look at the, remember, I want to show that S and the point of intersection of these two, that one, and that, those are the 3 points. I want to show that they are collinear, okay? And I said that we are going to use projective geometry and the theorem on cyclic hexagons to prove it. We have 6 points on the hexagon, and I am going to now check to see these points. Are they intersection points? S is the intersection of IN and HM. I'm going to use the red points because I know those red points are points on the circumference. Right. And I'm going to look at these 6 points which are on the cyclic hexagon. So I'm going to use those 6 points all the time. Now, what about T? Well, by T, I mean this point here. Let's call this point here T. There's no place here. That is why I didn't put a T here. All right, so this point, this shaded point. Now, you'll notice that this point is an intersection of 2 chords, namely IK, if you extend it, and HL, IK and HL, they meet at this point here. Right? I have to use those points on the circumference to get the sides of my hexagon, right? So that's T, and we wanted to prove that ST and C are collinear C, is it an intersection of any two sides of the hexagon? Yes, C is, we just proved that C lies on, K lies, MKC is a straight line. So now we can see why we had to do that, because MK produced gives you C, and also NL produced gives you C. So MK and CL, they intersect at C. Now, so now we've got all these points, I, N, M, and all these things are all now the hexagon. Now we have to look at, we will have now what we call this crossed hexagon. So let's start with IK. Now, if you remember, we said blank HL. Right. Then we took IK intersects HL. So this gives you your T. Now we still got two more points here. Now what shall I put? The 2 points which are missing, I, K, H, and L, are M and N. Right? Now we have, as far as H is concerned, you have an MH, you see? So let's put the M here. MH, miss a point, and you have to put the last symbol here, namely N, and come back to I. Right. Now, this way, let's just see, IK intersect HL is your T, right? Okay, we got that. KM, miss a point, intersection LN, there it is. This is your C. And then you have MH, miss a point, NI intersect NI, MH intersect is S. Wow. So there it is. You've got that this is a cyclic hexagon. And according to the theorem in projective geometry, these 3 points are collinear. Right? And that just becomes a sudden and abrupt end to this problem, because that was what we want to prove, that S, that, and that are collinear. So I got I, K, M, H, L, and I actually constructed Y. When I saw this for the first time, I said, where the heck did they take this from? Why are they going all over the place? But there is a logical way of doing it, because we need to get to show that these 3 points are collinear. So you have to look at which chords of the circle intersect at these 3 points. And once we identify those chords, we had to identify the 6 points first, right? The HI were natural, those two, and those two we introduced. And as you can see, it's a very difficult problem, even at IMO level, I think. But I'm sure there are people around the world who can solve this problem. I had to study it to understand it. Okay, we stop there. Thank you very much for listening.